Hello. This is the show where we're gonna make it make sense, or we're gonna try to at least. So here I've got y equals x, but it goes all the way to infinity comma infinity, and I'm gonna say that as a function, it's gonna be continuous there. I'll go in a little bit more detail. So we're talking about our space is gonna be 0 to infinity, including infinity. What is infinity here? It's just a name that we're giving to a new element. So it's not one of the non-negative real numbers, it's this new element. We're going to add it in. And in order to talk about continuity of the function f of x equals x, we're going to need a topology on this, and I'll talk about that soon. But here's the function that we're interested in. So, of course, that means f of infinity is going to be equal to infinity. Pretty cool, right? And we're going to claim that f is continuous. So what is a topology? Well, it's a collection of subsets of this. So for example, let's say our topology, we'll draw it with T. We're basically going to put a bunch of subsets in it. So for example, anything of this form is going to go into the topology. So in other words, if we start at 0, or if we pick a point alpha along the line, so here's our line down here, this is 0, this is infinity. If I pick any point alpha, then everything below alpha is going to be in our topology for any point alpha that I choose. Also, anything above alpha is also going to be in our topology. So that's going to go in there. And we'll go ahead and have a little bit of redundancy here, but we'll just say that the entire space is going to go in our topology, and the empty set, the set that has nothing in it, is going to go in our topology. Also, any intersection of sets of this form is going to go in our topology. So for example, if I pick a point beta, and I take everything above beta, and then I take everything below alpha, and I intersect those, I'm just going to be left with the overlap region, which is just going to be the open interval like that. I would have actually liked to switch the letters a little bit. I'll go ahead and switch the letters over here, but you can imagine how that would go. So anything of this form is going to be in our topology. Now the last thing I want to do is any combination of sets of these kinds is going to go in the topology. So for example, if I had a set 0 to 1, and I had a set 2 to 3, and I had a set 5 to infinity, then I could combine these sets so that I would have, if I was to draw what that would look like, this is 1, 0, 2, 3, 5, infinity. So if I shade in that region, shade in that region, shade in that region, all of that, considering this whole thing as a single subset of the interval 0 to infinity, that's going to go in the topology as well. In this case, I'm taking the union of these two sets with the union of this set. All of that is going to also go in the topology. Now in this case, I combine together 3 open sets to get another open set, but I could actually combine infinitely many open sets together to get another open set. And that means I'm actually going to have open sets that are going to be quite advanced, so to speak. I could have like really weird like stuff going on with the infinity stuff. But yeah, so that's basically the idea, is that anything in the topology is called an open set, and any combination of open sets is an open set, any finite intersection of open sets is an open set, the entire space is an open set, and the empty set is an open set. And so the topology is this collection of open sets. That's what an open set is. It's just an element of the topology. So of course, intuitively, we have a pretty nice thing because the open interval 1, 2 is going to be considered an open set because it is in the topology after all. But less intuitively for some, this thing is also going to be considered an open set. Now, if we were talking about the standard topology on the real number line, this thing would not be an open set because it is like this half-open interval. But if you look at this space, because 0 is at the very end of the space, it's okay. This is going to be an open set. All right? So what about continuity? Well, we say a function is continuous, so maybe it goes from A to B. If I pick an open, so A is going to have some topology on it, and B is going to have some topology on it. So really, F is taking us from a topological space to into a topological space. So when would I say F is continuous? Well, if for any open subset, for any open set of the topological space over here, that if I take the inverse of F of that open set, I end up with an open set over here. So in other words, open goes to open under the inverse of F. Then I say, if this is always the case, that F is continuous. For example, if I had open going to not open, then for anything, if I could find a single example where open goes to not open under the inverse of F, in other words, if an element of this topology, and then I apply the inverse of F, and I get something that is not an element of this topology, so essentially I've escaped, right? I began in this topology, but then I sort of didn't go over into this topology under the inverse. I sort of escaped. Then F is not open. Or sorry, F is not continuous. So what about f of x equals x? Well, we defined our topology, right? We had this is the space, and then we defined the topology on it. If you kind of put those in parentheses, this is like the topological space. So f is taking us from 0 to infinity into 0 to infinity. So it's taking us from a topological space into that very same topological space, and it's always mapping a point x to that very same point x. Well, it stands to reason that if I had set A, and I take f inverse of A, I'm just going to get A back, because f is the identity. F inverse is also the identity. So yeah, A is just going to go to A. So if A is open here, and I get A back, well, it's still open. It's the same thing, right? If A is open, then A is open. So open went to open. And that's the only thing we require, right? If open goes to not open, that means A goes to not A. But no, A always goes to A. So in fact, the identity function from any topological space into itself is always going to be continuous. So we can indeed say that f is continuous, and in particular, f is continuous at x equals infinity. Pretty cool, right? If you have any questions, feel free to ask, and I hope you enjoyed it and found it interesting. Thank you, and goodbye.